So
we are getting close to 1 o'clock. Should we start letting people in?
Okay. Just wait a few seconds. Okay. So welcome again to this new Imaging One World talk. And a big thank again to the Royal Microscopical Society for the organization, together with Curti, Alex, Stephanie, and of course Nick, who today will run our unique Mentimeter quiz. Our world-known Mentimeter quiz. So I'm Alessandro, and today we welcome Dr. Lixue Shi, and all of you joining us from across different time zones. Lixue received her degree in chemistry from Peking University in 2014. She then completed her doctoral studies on Raman at Columbia University. Lixue continued her work as a postdoctoral scientist in New York, pushing sensitivity and throughput of vibrational imaging tools for biological applications. So Lixue is now establishing her own group at Fudan University in China. So big congratulations to her that next month will start her own group. And she will continue working on vibrational imaging tools, but with a specific focus on applications for pathology and clinical medicine. So I'm looking forward to her talk today entitled Super-multiplexed vibrational imaging for 3D spatial biology. And Lixue, the stream is yours.
Thank you, Alexander, for the kind introduction. First, I want to thank all the organizers for hosting this great lecture, and I'm also a big fan of this event. Today, I'm very excited to have this chance to introduce you some of my postdoc work at Wei Ming Lab in Columbia University. Essentially, I will talk about some recent progresses on vibrational imaging and how they contribute to probing three-dimensional spatial biology. Okay, one of the grand challenges in biology is how to understand the immense complexity. Indeed, a recurring theme in biology is that a large number of interacting players are interacting at every scales, from a protein network to interacting organelles, to different cell types in tissues, and to regions in the organs. So in order to understand the organization of complex biological systems, multiplex measurements are critical. Moreover, cells and organs are inherently three-dimensional. Therefore, 3D spatial context is essential. Ideally, higher spatial resolution will provide the opportunity to identify more sophisticated structures and also greatly increase the information content. So altogether, imaging technologies that can measure multiple protein markers across 3D space at fine spatial resolution are highly preferable to visualize diverse cell types and also physiological states within complex biological systems in situ. Recently, to probe in situ biology, several multiplex imaging methods have been developed relying on antibodies directed against protein biomarkers. There are two main categories. The first is cyclic fluorescence with fluorophore or DNA-labeled antibodies. And the second is mass spectrometry, which use metal probes. Despite the rapid growing of this multiplex image pool, current approaches can only be applied to thin tissues with a thickness below 100 micron. Moreover, the spatial resolution is generally limited to the optical diffraction limit, making them hard to visualize some nanoscale fine structures. So towards the aim of probing 3D spatial biology of a complex system, we provide an alternative way as vibrational imaging. Indeed, fluorescence is a bottleneck for multiplexity. Typically, no more than 5 colors can be detected simultaneously by fluorescence, considering the severe spectral overlap in emission and excitation spectrum. This is also known as fluorescence color barrier. Therefore, cyclic staining and images usually are required for a fluorescence-based multiplex imaging approach, which certainly brings tedious sample preparation and error-prone image alignment and registration. Different from fluorescence, vibrational peaks are 50 to 100-fold narrower. Hence, vibrational methods pose a fundamental advantage for multiplexing in one shot, overcoming all these issues related to the cyclic way we just mentioned. The potential of Raman imaging for multiplex detection is actually not new for the field. For instance, back to 2002, Merkin group has coupled Raman spectroscopy with nanoparticles functionalized with oligonucleotides as well as Raman active dyes to perform multiplex detection of oligonucleotide targets. However, existing Raman reporters just rely on those commercial fluorescent dyes. Their signature peaks are all in the so-called fingerprint region. As indicated by this Raman spectrum of the cell sample, the fingerprint region is already very crowded and contains Raman backgrounds from endogenous biomolecules inside cells. So one grand challenge for developing Raman-based multiplex imaging tool is the lack of chemical innovations. On the other hand, standard Raman techniques are still away from a general imaging platform. As you may know, Raman is a notoriously weak effect that is about 10 to 12 orders of magnitude smaller than fluorescence. Therefore, standard confocal Raman requires hours to days for imaging acquisition. In addition, the parasitic ultrafluorescence background from the biological samples easily overwhelms the weak Raman signal. Surface-enhanced Raman scattering source offers a solution to overcome this drawback by enhancing Raman intensity in the presence of metal nanostructures. While source is a powerful method to provide structure and dynamical information, also unravel the single molecule sensitivity. Its strict reliance on the metal nanostructures hampers biocompatibility. Typically enhanced Raman scattering TERS coupled Raman spectroscopy with scanning probe microscopy. Similarly, TERS requires surface touching of a plasmonic tip, which could also be invasive for biospecimens. So both techniques lack the good biocompatibility. Considering all these challenges we mentioned, we have to first take care of multiple aspects in the development of sensitive multiplex Raman microscope. First, how can we generate as many Raman colors as possible with a more systematic chemical design? Second, if we can work out a way to improve the sensitivity of Raman detection. Finally, how can we integrate all the modifications and improvements both on the probe and spectroscopy side to real biological samples such as tissues? Will relate to the engineering on probe labeling and the sample processing. Let's start from the microscope part. Instead of conventional spontaneous Raman scattering, stimulated Raman scattering, SRS for short, is a nonlinear process achieved through stimulated emission of radiation. This effect was first discovered in 1962 by Woodbury and Ing when they were studying the ruby laser. So instead of using a single laser as in spontaneous Raman, Stimulated Raman requires a coincidence of two lasers, one for excitation named pump beam and one for a stimulated emission named Stokes beam. When the energy difference between two beams matches with the vibrational energy of the chemical bond, the Raman transition rate is facilitated proportional to n Stokes, that is the average photons in a mode of the Stokes laser, which is roughly 8 orders of magnitude. Of note, such a large quantum amplification is already comparable to the electromagnetic enhancement factor in surface-enhanced Raman. SRS was first developed as a spectroscopic method in nature, and converting SRS for the purpose of microscope is a cornerstone. In 2008, the Lixue group in Harvard first optical systems with high-frequency modulation and locking detection. Technically, an intensity-modulated Stokes beam is collinearly combined with a pump beam to be focused onto the sample in a synchronized manner. As shown here, the Stokes beam intensity is on-off modulated in time. When the energy difference between these two lasers matches with the vibrational energy of the chemical bond of interest, the chemical bond is vibrationally excited. At the same time, one pump photon is annihilated and one Stokes photon is created. Effectively, the pump laser intensity is decreased in the presence of Stokes photons, and it is called stimulated Raman loss, which is a SR signal to detect. Therefore, by optically filtering out the Stokes photon and detecting the pump photon only at this modulation frequency, the pump laser intensity change delta IP corresponding to the SR signal can be detected. Because this delta IP is detected on top of a very strong pump laser intensity, high modulation transfer scheme up to megahertz modulation is get rid of the low frequency laser noise, achieving short noise limited detection sensitivity. So currently the reported detection limit of SRS for the CH bond is about 15 millimolar, and for alkynes, the carbon-carbon triple bond is around 200 micromolar. This sensitivity is already very good, but still not enough to detect some low abundant biomolecules. But the invention of SRS microscope largely addresses the limitation of Raman techniques on biocompatibility, and hence provide a general bioimaging platform for studying biological systems. As shown here, since its invention, SRS imaging has been applied to provide chemical maps of live mammalian cells, whole organisms such as C. elegans, tissue sections, and it is also applicable for non-invasive diagnosis. Also, if we want to further enhance Raman scattering, the use of so-called electronic resonance enhancement in the molecule is an alternative mechanism named resonance Raman. So resonance Raman employ a laser light with the frequency close to the energy required for the electronic transition of a compound. As large as 7 orders of magnitude enhancement factor has been measured for this rhodamine 6G pigment before. We just mentioned the sensitivity of Raman is for detecting low abundant biomarkers, and the SRS process accelerates the vibrational transition and greatly improves the sensitivity. But all previous SRS imaging work are on the so-called non-resonance region. To further improve the detectability, we will integrate electronic resonance effect we just introduced into SRS and developed a method named electronic resonance SRS, epr-SRS. So by carefully tuning the absorption of chromophores close to, but not identical to the SRS excitation wavelength, which is a Pong beam in our case, we can acquire Raman spectrum of far-red chromophores like L740 dye and the sin 7.5 with a sufficient signal-to-background ratio. As a result, the epr-SRS process can drastically improve Raman scattering cross-section by up to 10 to the 5th fold. Thus, the detectability of Raman active chromophores in epr-SRS has been leveraged to a sub-micromolar level. Then, with this ultra high sensitivity of epr-SRS, we are now able to measure low abundant biomarkers inside cells with a decent signal-to-noise ratio. To identify specific biomarkers, we can use a typical lysine-directed NHS ester labeling approach to conjugate our Raman dyes to antibodies or oligonucleotides. With antibody-targeted immunolabeling, specific proteins such as membrane markers or cytokeratin can be visualized on the surface of breast cancer cells. Moreover, by conjugating Raman dyes to a short nucleic acid probe, specific RNAs with a complement sequence to this probe will be labeled through in situ hybridization and subsequently imaged by epr-SRS. In addition, our technique is generally compatible with living cells. For instance, we can probe the distribution of organelles such as lipid droplets and mitochondria in live cells. The spatial resolution of epr-SRS is comparable to a 2-photon fluorescence. So if you use near-infrared excitation, the lateral resolution is around 300 to 400 nanometer, depending on the objective you use. This allows imaging of subcellular structures such as microtubule bundles. Moreover, the nonlinear nature of stimulated Raman enables optical sectioning capability. Therefore, epr-SRS is capable of imaging tissues in a 3-dimensional form. As an example here, we demonstrated 3D visualization of astrocytes in the mouse brain tissues. So compared to the fingerprint region, a spectrally cell-silent window where no endogenous biomolecule vibrate will become more attractive for probe design. We also call this bioorthogonal window. Some triple bonds like nitrile and alkyne usually vibrate at this region. You may have heard the word bioorthogonal chemistry multiple times last week, which just received the Nobel Prize in Chemistry 2022. We were also inspired by a similar concept to design probes, which rarely exist in the biological system. As you can see, this is a cell spectrum. There is almost no background at this bioorthogonal Raman window. So back to the development of bioorthogonal Raman dyes to fulfill multiplex imaging purpose. We rationally designed and synthesized corresponding epr-SRS dyes. Each has a triple bond directly participating in the pi conjugating system with dancing identified as a promising scaffold. We named this dye palette Manhattan Raman scattering dyes, Mars for short. Our multidimensional color extension strategies can be understood with a classical description of vibration. So following the equation here, a manipulation of a nitrile bond mu can modify the vibrational frequency of nitrile on different Mars dyes. On the one side, substituting the core atom, the central atom of the chromophore, as well as gradually expanding the number of rings of the chromophore can fine-tune the nitrile frequency by affecting the electron density of the entire pi conjugating system, which is the key factor in this equation. Moreover, isotopic editing of the two atoms in the nitrile bond further enables Raman frequency modification by changing the reduced mass mu. Altogether, our mass dye palette offered rainbow-like narrow band single peak bioorthogonal Raman features, thus providing an optical super-multiplexity. So after functionalized Mars dyes with a linker and also conjugating them to antibodies, we achieved one-shot 12-color protein imaging on mouse brain tissues with epr-SRS. This type of application is real beyond the imagination for the Raman community before. Again, with all the developments on spectroscopy, probe chemistry, and labeling strategy, we provided a super-multiplex vibrational imaging platform as an all-in-one method for multiplex protein imaging. So in which antibody-targeted labeling and imaging can each be performed within a single round. With this established platform, we next leverage its utility in two directions by integrating sample engineering. First, towards the large-scale direction, we develop an approach called radiant for volumetric imaging of multiple proteins in thick intact tissues. However, in terms of thick tissue imaging as an optical technique, epr-SRS is still limited by light scattering in tissues. That is, in universal free space, all excitation light reaches the focus, but in very scattering tissues, in homogeneous scattering cause light rays to miss the focus and lost to signal generation and connection. Therefore, the typical imaging depth of SRS is below 100 micron in brain tissues. As you can see here in this graph, the epr-SRS signal drops significantly with the imaging depth. So in order to gain optical access inside thick tissues, tissue clearing has emerged as a powerful strategy by replacing inhomogeneous components with some special chemicals to make this biological specimen transparent. A group of chemical recipes have been built to clarify tissues from individual organs to even entire mammals. However, all these techniques were developed and optimized for fluorescence imaging. Their utilization in Raman dye imaging is underexplored. So here we aim to extend the epr-SRS to 3D with tissue clearing protocols, particularly optimized for Raman dyes. To achieve this aim, I started from screening established tissue clearing protocols, and we found an organic solvent-based method called DISCO, and its derivatives works the best. So on top of DISCO clearing recipe, we further modify the we first modify the lowering the temperature to 4 degrees, and also screen on the antioxidants for better preserving mast dyes. So with this new we call it Raman DISCO clearing recipe, the imaging depth was greatly improved. Here we demonstrated 1 millimeter thick mouse brain tissue imaging by looking at the Raman dye stained GFAP marker, which is a marker for astrocytes. The imaging depth of SRS was then extended for more than 10-fold. Encouraged by these results, we have now accomplished one-shot imaging of 11 different targets in 1 millimeter thick cerebellum section using Raman DISCO clearing. As indicated in this graph, our Raman method opens up the door for high content, large context protein imaging, as this yellow area indicate, which existing methods cannot do. So this highly multiplex volumetric results can enable systematic analysis to explore spatial features. For example, we can calculate Pearson correlation coefficients between different protein pairs and do the clustering for different anatomical layers of the brain. This can provide an overview of protein-protein correlation. In addition, the underlying architectures of some specific subregions can be visualized using a network representation. This is helpful to find some important targets of biomarkers. Also, thanks to the rich information in a large volume data set, some 3D-based analysis is also doable. In the previous Pearson correlation analysis, we noticed strong correlation between vibrating and GFAP. Actually, GFAP and vibrating are two major intermediate filaments for astrocytes. So to study the spatial features of vibrating GFAP correlation, we further segmented our data set to vibrating plus GFAP plus, vibrating plus GFAP minus, vibrating minus GFAP plus cells in 3D space and performed a cell compositional analysis. For example, we found that the majority of astrocytes, which is the GFAP positive cells, co-express vibrating. This may suggest an early stage of glial development, as we are using postnatal day 15 mouse, which is also coincident with the time window of the myelination process. In addition, we can measure the distance between different cell subtypes and its closest blood vessel, which is called the cell-to-vessel distance. This is also a very important parameter in the organization and the development of the central nervous systems, and which has to be accessed from volumetric images. Overall, our volumetric multiplex dataset will enable system analysis of protein interaction network with spatial information. In contrast to going large, another direction we see unique advantages of our method is pursuing higher spatial resolution. We also developed a method called MAGNIFIERS as coupling SRS with expansion microscope for profiling ultra-fine nanoscale structures. As we introduced at the beginning, as an optical technique, SRS microscope is still constrained to diffraction-limited spatial resolution at around 300 nanometers. And the existing strategies for super-resolution vibrational imaging are mainly based on a regulation of the point square function, either with a higher order nonlinearity of Raman scattering, which intrinsically have a narrower point square function, or erasing the edge by donor beam laser depletion. But despite extensive efforts along this direction, usually sophisticated instrumentation is required, and only very moderate resolution improvement, typically less than twofold, has been achieved. Therefore, the utilization of these techniques in biological specimens is very limited. Over the last half decade, a sample-oriented technique known as expansion microscope has emerged as a non-optical means of super-resolution. It achieves sub-diffraction-limited resolution on a conventional scope through physical expansion of tissue samples, which is embedded in a water-soluble polymer gel. So after expansion, previously unresolvable structures can be clearly visualized with a diffraction-limited optical microscope. This is particularly powerful for tissue imaging, as most tissue samples are already dead and fixed. But expansion microscopy was also initially developed for fluorescence. Again, similar to tissue clearing, expansion microscope has never been, there was little exploration has been done for vibrational imaging. So in collaboration with Professor Leon Zhao at Carnegie Mellon University, we integrated Raman with the most recent advancement in expansion microscope. 3 major optimizations were applied in our new expansion method. First, methyl-acrolein, which is a very active chemical, was employed as a part of the monomer solution to efficiently attach biomolecules to the growing matrix during the polymerization step. In this way, we eliminate the need of stepwise reaction of anchoring and polymerization used in previous design. Second, rather than strong protease digestion, we treat the gel-embedded specimen in a denaturant-rich solution together with heating for homogenization. So this will ensure maximum retention of biomolecules in the gel. Thirdly, the hydrogel recipe was reformulated. With our new recipe, isotropic physical expansion up to 10-fold is allowed in a single round with very good sample compatibility. As a summary, this new expansion microscopy strategy achieved a favorable balance between biomolecule retention, expansion factor, as well as sample generality. So by combining SRS imaging with the new expansion framework, we lay out an approach named magnifiers. Then how does magnifiers work for tissue imaging? We first measure the protein retention rate of this new protocol and compared it with other widely used expansion microscopy approaches in fluorescence. First, we found a nearly 100% protein retention rate. Also, if you compare the pink with the yellow bar, a substantially higher retention rate is achieved with our method compared to the protein retention expansion microscopy recipe. Moreover, those structure patterns are much better preserved after changing the proteinase to detergent for homogenization. Additionally, this high biomolecule retention also ensures optimal sensitivity and effective resolution after expansion. Second, we show this magnifiers is compatible with common and multiple tissue types. This approach works well even for some mechanically tough tissues such as kidney and the liver. And also going beyond this freshly preserved cells and tissues, some archived samples such as FFPE sections of human brain, kidney, and spleen are also very compatible. So magnifiers can provide niches that are complementary to existing SRS or expansion microscope imaging alone. On one side, magnifiers complements fluorescence-based nanoscope, which lacks chemical specificity and can only image like 4 to 5 colors. On the other side, it offers a simple and general way to achieve super resolution Raman imaging. More specifically, magnifiers revitalized a full spectrum of utilities of SRS imaging into the subdiffraction regime. First, magnifiers will support label-free nanoscale imaging of endogenous biomolecules, including proteins, lipids, and DNA. It is also useful for high-resolution metabolic imaging of protein aggregates in cells labeled with some deuterium substituted amino acids. Finally, MAGNIFIERS enables mapping the nanoscale locations of multiple protein markers in mouse brain tissue by applying multiplex Raman labels and some conventional fluorescence probes. So, as to echo with the theme of multiplex imaging, I hope to further elaborate multiplex nanoscale imaging a little bit. Multiplex super-resolution protein imaging in 3D tissues is technically very challenging. Cyclic fluorescence method is highly artifact-prone in this scenario because nanoscale fine structures are more vulnerable to some nonlinear histological changes among cycles and will demand higher precision on image alignment. But with our expansion Raman imaging, we currently demonstrated a one-shot 8-color nanoscale imaging. Notably, our approach has the strength to unravel clearly distinguishable pre- and post-synaptic labeling, which are usually overlapped spots before expansion. For example, the separations between synaptic vesicle markers, synaptophysin, and post-synaptic marker PSD95 is clearly visualized, and we also quantitatively analyze the distance, which is around 120 nanometer on average. This result is very close to the prior measurement of around 150 nanometer using super-resolution fluorescence imaging. So altogether, based on the super-multiplex vibrational imaging platform, we developed 2 technologies here for as a large dimension protein imaging across different biological scales. Indeed, expansion microscope itself is a hydrogel-based tissue cleaving approach. Therefore, these 2 directions can actually converge as our holistic optical imaging platform for really integrating biological structures from nanoscale to millimeter scale. Overall, the rising vibrational imaging methodologies is promising to open exciting applications to probe spatial patterns of ultrastructures with high content over a long distance, such as for neuronal tracing. So in the end, I want to thank my advisor, Professor Wei Ming, for his guidance and advice throughout the journey. Also, I want to thank all my collaborators at Columbia and Carnegie Mellon. Also, many thanks to the funding agency to support this work. By the way, I will start my own lab soon at Fudan University, and we are recruiting at all levels. So feel free to reach me if you have interest to talk more. Thank you again for your kind attention. Yeah, I'm happy to take questions you may have.
Right. That was a wonderful talk. Thank you very much. Now we go into the usual Mentimeter Mentimeter challenge. All right, so you should see the link there in the chat. So try and join that. If you stop sharing, I will put the Mentimeter quiz up. Is that okay?
Yeah, sure.
Thank you very much.
Sure.
Great.
Yeah, I've stopped the screen sharing.
Oh, here we go. Right. Now let's see if come on. I can get that up. Share screen.
You have this kind of internal.
There we are. Oh, we've got a few.
Oh, yeah, brilliant.
Few participants, or 4 participants so far. So let's see if a few more people can join in. Right. That one. Oh, got another one joined. 5 people on, so I think if we can get one more person in, we can give it a start. So, right, let's give it a go. Anyone else want to join? Okay. Illuminate. All right. All right. Well, we're gonna kick off with 6 participants. So, question number 1. Fingers on the buzzer. So the faster you answer, the more points you'll get, and you'll get to win. Then the winner gets to go home with a fantastic fold scope. So I'm just going to start the countdown. Here it is. Answer fast. What is the selection rule for Raman spectroscopy? It's question 1. A change in the dipole moment of the molecule during molecular vibration or rotation, or a change in the polarizability of the molecule during molecular vibration or rotation. Okay, and the answer is the polarizability. So well done to the 4 who got that right. Excellent. And
I think just reading this and the time you give them was kind of a
that's
challenge.
good. Yeah. Well, I've got to, let's see what the leaderboard has. Oh, Ambriel, you are the winner. Barefoot Contessa next. Jan and Cake on your tail. Right. Next slide. Number 2. Right. Enter. Okay, again, as fast as you can. What is the Einstein B coefficient? That is the absorption rate, spontaneous emission rate, stimulated emission rate, or scattering rate. So I think the physicists in the audience have probably got an advantage on this one, but let's see. Everyone, pretty much. Oh yeah, stimulated emission. Well done. Let's see how we're doing on the leaderboard now. That might be enough to change things. Okay. Beyonce is catching up, I think. Oh no, Cake and Yang are catching up. Beyonce has just got into the game, I think. Okay. 3rd question coming up now. And another tricky one, I think. Let's see. What is Abbe's resolution limit of optical microscopy? Is it the resolution is lambda over n, or the resolution is lambda over 2na, or resolution is 2 lambda over refractive index times na, or resolution is lambda times refractive index times na? Oh, yep. A lot of people are on the ball today, faster than I can even say it. Okay, so let's see how the leaderboard is now.
It's kind of nice how the basics come back in these very advanced lectures.
Oh, look. Oh, Ambriel, you're still maintaining your lead. Obviously, the first question has set you up for the whole match, but Jan and Cake are getting closer. Beyonce's there as well. Okay. Got a couple more questions. Question 4. Let's see how we get on with this one. Which is correct for resonance Raman scattering? The excitation wavelength is within the absorption band of the molecule. The excitation wavelength is within the emission band of the molecule, or the excitation wavelength is close to the size of the molecule. Which of those is the correct answer? And it is within absorption. Okay, so again, 5 correct answers there. Let's see what happens now. Ooh, this might be enough to change the leaderboard. Let's see. Yeah, you are the winner. Okay, Ambriel and Beyonce, you're still within reach. So I think it's all down to the last question, unless Jan can hold them off. Okay, so again, answer as quickly as possible to get the most points. Here we go. What's the major source of photon noise in stimulated Raman scattering microscopy? Is it photon shot noise, Fano noise, fixed pattern noise, or read noise? And this is a really tricky one. The answer is photon shot noise. Wow. Okay. Everyone got that, so it's down to speed now. Let's see who was quickest on the buzzer. All right, here's the leaderboard. Ooh, yeah, you may well have held it. Let's see. Yep. Jan or Jan, you are the winner. Please make yourself known to the organizers. You can just that was a great quiz.
Hi. Oh, not sure if you can see me right there. Oh, you can hear me.
So close this time from Georgia. That was a very good quiz. Right. So having done the quiz, giving you time to we've lost our speaker. Are you still there?
Oh, she's there. She's there, it's okay.
Yep, I've just lost the picture. Anyway, it's time for questions.
You lost it, Nick. But
I lost it.
It's
Right.
actually frozen also for me.
So let's have a look at if we have any questions, or if anyone wants to kind of ask the question in person, maybe that's your opportunity as well. If you want to unmute.
Well, I definitely.
Jan, I mean, maybe you want to ask a question too. We can celebrate your winning, but we may have a question as well.
Yeah, sure. I've heard about expansion microscopy before, especially with regarding fluorescence. So I was honestly quite surprised that you can achieve that without getting any background noise from basically matrix that you introduce into the sample. So do you actually get some signal unwanted signal enhancement, unwanted pollutant in the original sample, or are you able to somehow mix it out? Maybe I didn't get that.
Is our speaker still there?
I thought so. She looked. Oh, maybe you're right. I mean, not just you lost it. We did lose our speaker.
I can see
She looks like she's frozen.
Yeah, she looks frozen here.
The expansion microscopy, well, I think it originated probably at Boyden's lab. And
you are.
I don't know
Okay.
who's is she back?
She's asking if she's frozen.
Yeah, she is frozen. Sorry.
Let's see if we can get her back. It's a new losing our speaker. Normally we don't do that. Normally the disaster happens in the quiz. But all right, let's see if we can get Lixue back. Oh, on our way back. Okay, I can see I can see this. There's something going on in the chat, so we might get her back in a minute. All right, you can hang on. Oh man.
Actually, this for me, speaking through Zoom with China is a record. Usually my conversations are dropped after 40 minutes for whatever reason.
Right. So this was a link all the way to China. Wow. Excellent. Surprising.
Maybe.
I think we had Australia before. I think we've maybe had Australia for at least 4 participants. Okay.
So I think it would be good if she would answer, because
well, I feel yeah, we should give her the opportunity. Let's see if we can.
Lixue could actually message us if it's not working.
Yeah.
Talking to us would be possible.
Maybe, you know, maybe we can also move some question who wants on Twitter.
Yeah, we can.
Anyway, I just while we are trying to see, I mean, is certainly was one of the most interesting for me talks that I watched on Raman in the last few years. I mean, particularly because there were things that I can follow up in the literature. So it was very cool. This was very nice.
Yeah, no, I agree. Here we go.
Yes, hi.
Right. Jan, welcome back, Lixue. We can all see you now. I don't know if we can hear you. Can you try saying something?
Yeah, can anyone
Perfect.
hear me?
Yes,
Yeah.
perfect.
Oh, that's nice. I think, yeah, I think just ask a question about if I need to do some unmixing. Did I get it right?
think so.
Basically, as in what kind of a because I imagine that the matrix is gonna in the expansion microscopy is gonna generate some signal that. So my question is how do you get rid of that signal?
Yeah,
For
that's
instance, if you're scanning stage region or whatever.
Yeah, that's actually a very good question. Yeah, we have to do some unmixing. This is because it's very hard to control that the intensity of all the biomarkers at a similar level. So even the bandwidth is very narrow for Raman. If the intensity vary too much for two adjacent markers, you have to do unmixing. Yeah, so we will do some unmixing in our samples.
Thank you.
But the principles may not be all the background source may not be the same compared to fluorescence, because for fluorescence you may know the noise is the square root of your signal. So once you have very strong if you have a very abundant markers, it will easily like overwhelm the adjacent weak channel because of the strong noise introduced by this marker. But for SRS imaging, the situation is different. Our major noise is the laser noise. So if it doesn't matter if you have a strong or weak signal, the noise level is almost similar because you are like beating with a strong laser short noise. That's why I asked the fifth question on the quiz. So it's a kind of different compared to fluorescence.
And when you do the chemical clearing, is it causing issues with generating more noise because of the chemicals you're using for the expansion or the clearing? That doesn't cause any greater issues than fluorescence or?
First, because we designed the probe in this way, we use a triple bond as our indicator. So it normally your most chemicals don't have triple bond, so they won't bring many Raman backgrounds. On the other side, we also do some screening. Yeah, we will screen. We will when we optimize or when we like build up the tissue clearing recipe, we will do the first round screening to make sure there is no like spectral influence from the solvent or from the tissue clearing chemicals, because it is very abundant. So yeah, we need to make it low.
All right. Any more questions in the chat? Does anyone else want to put their hand up? Okay, because I just want to go all the way back to the sort of very basics. What laser lines are you using on your instrument? Just out of curiosity.
So we're using near infrared laser for excitation. Our pump beam is at 900 to 950 nanometer, and it is a tunable beam. And our Stokes beam is a fixed beam, which is like over like 1 micron, around one micron.
Is that from a Thai sapphire laser or something similar sort of technology? Okay. Yeah.
So you can use Thai sapphire laser, and there is also a fiber laser source.
Yeah. Okay. All right. Is that synchronized? Is that from an OPO as well in there? Or?
Yeah, it's from OPO. Yeah, because we need to use high repetition rate.
Yep. So sort of whatever it is, 80 megahertz or something like that.
Yeah, 8 megahertz, 80 megahertz.
Yep. Great. Any other questions from the panel, from the audience out there? No?
I guess the probes you're using, they are all available, or they, I mean, how could people use them? Because we all want to do what you do, so.
Yeah, that's a very unfortunate thing. Yeah, we try to commercialize it, and Sigma have talked with us before, but they have do some like surveys and investigations. They think the market is still not enough. So we hope in the future this can be commercialized.
Okay. You should all send out questionnaires so we can all say we want them. So the commercial companies are interested, yeah.
It's one of these situations where there is no market without the probes, but they commercialize the probes if there is market. So
yeah, it's a dilemma, right?
Yeah, but we have the market.
Okay, sorry, did we do this one? There's a question in the chat now from Sophia. Sophia, if you would like to ask your question first, then you can unmute and ask it.
Yeah, I can. I can read the question. Yeah, Sophia asked, like, she wondered when using the technique to image cancer in vivo, how long would the process take? So for SRS imaging, it can be applied for in vivo applications, but for our epr-SRS version, which relied on many dyes and probes, some sample processing and labeling strategies is not compatible for in vivo studies. So if you want to just do some label-free imaging on like to see where the protein is and where the lipid is, I think the process is very rapid. You can even do like video rate acquisition. But for if you are interested in some specific biomarkers like imaging a specific protein or RNAs, I think it is still away from in vivo.
Right. Okay. Good.
Can I have a very fast question?
Yeah.
More than a question is just to prove my ignorance in chemistry. So this carbon nitrogen triple bonds that they give this opportunity for multiplexing and so on. I was wondering, is there any possibility that we will see genetically encoded molecules that are exploiting these bonds to show the right spectra?
Yeah, I couldn't hear very clearly, but I somehow, I guess you're asking if there is a genetic version of the probe, right?
Correct.
So I think that's a very difficult one, because you need to engineer some proteins. Like if there's some proteins that can modify or can introduce a nitrile to a specific biomarker, that will be possible, I think. Yeah. Also, another challenge is if you want to do multiple channels, yeah, how can we like train these proteins to identify different markers? That's another issue. So yeah, this is a really exciting direction, and we hope if protein engineering can really help us here.
Okay. Thank you.
Good.
Thank you.
So if we do not have any more questions, I suggest we actually give our speaker another big thank you, and we'll close for the day. So Lixue Shi, thank you very much for your talk. That was really interesting, and I'm going to go and
fantastic talk.
Yeah.
Thank you very much.
Thank you all for
this really inspiring.
thank you all for this great chance.
Thank you.
We see more about that. Thank you.
Bye.
Bye.
Bye-bye. Thank you.